seen that the MOSFET transistors can be used in switching applications, switching currents, voltages, and power while having zero input gate current. The other applications of MOSFETs are in the amplification of small signal time varying signals. Okay, uh, the MOSFET in conjunction with the other circuit elements, they can be used to amplify the small time varying signals. You see in figure 47 over here, uh, you have a common source NMOS MOSFET configuration. Why it is common source? Because you see with regards to the input and the output, with regards to the input and the output, you have the source that is common. Okay, the output is being taken from the drain, the input is applied to the gate, so the source is common. So it's a common source configuration. Okay, CC is a coupling capacitor through which you are superimposing an AC input voltage. Okay, a sinusoidal, let's say an AC input voltage is being superimposed. R1 and R2 forms the biasing for the gate voltage. Okay, there's a voltage divider over here which determine how much VG is there. So if VG over here is greater than the threshold voltage of the NMOS transistor, this is greater than VTN, or you can write this as VGS because the source is at 0, or VGS is greater than VTN, then your transistor is on. So it is either in saturation or non-saturation. Okay. So if you see, if VGS, if your VDS, the VDS over here, the drain to source voltage, is greater than VDS sat, the transistor is biased in saturation region. Okay, so VDS is greater than VDS sat, which is equal to the difference of VGS minus VTN. The transistor is in saturation region. So basically, you see the applied gate voltage, the applied DC gate voltage is determined by the ratios of the resistors R1 and R2, determines whether the transistor is in the saturation region or in the non-sat region. Okay, so for example, the VDS over here, VDSQ, is greater than your this. So this dotted curve is showing you the points for the given VGS, the transition points where the transition occurs from non-sat to sat regions. Okay, so for this VGSQ, this is the transition point. Okay, and if the VDS is beyond this point, then you're operating the transistor in the saturation region. So in saturation region, the current is not dependent on VDS. Okay, so we have talked this time and again. So over here you have this IV characteristics, and then you have the DC load line. So DC load line implies you have 2 points. Okay, this is for VDS 0, and this is for where the ID is 0. So if you see at the output, the DC equation becomes the load line equation is VDD minus IDRD equals to V naught. Okay, so VDD minus IDRD is your V naught. V naught is VDS. Okay, so I can write this V naught as VDS. Okay, so you have a linear relationship with the current ID and VDS. These are the two variables. Okay, RD and VDD are constant. Okay, VDD is your supply at drain, RD is the load resistance at the drain. So you see when ID is 0, VDS is VDD. This is this point. Then when VDS is 0, so this point is your VDD by RD. Okay, VDD by RD is your DC current ID. So this determines the load line. So if you connect those 2 points, so wherever the intersection occurs, this happens to be the Q point. The intersection between the IV curve, which so for each VGS we have a similar IV curve. This is my VGSQ. This is where the intersection occurs, and we call this the Q point. The Q point determines your drain source voltage and the current that flows from drain to source. These are the DC quantities. These voltages and currents are DC quantities, and this determines the Q point. Okay, the Q point again is the intersection between the load line. This is your load line. This is the load line. Intersection between the load line and the IV curve. IV curve for there, and you have a family of IV curve for each VGS. Okay, so you have 3 different VGS which are determining the Q point. Okay, all right. So you see, VGS is all that determines the transistor operation. If VGS is greater than VDN, well, the transistor is on. Then it is either in saturation or non-saturation. So if VDS sat, which is given by VGS minus minus VDN. So if VDS comes out to be greater than this term on the right hand side, then you're in the saturation region. And on this curve where the load line is intersecting, which is being determined by VDD RD and VDD, so these 2 points they will determine the operation of MOSFET. So figure 47 shows the MOSFET small signal amplifier. It is a common source. It is in common source configuration in which the time varying signal is coupled to the gate through a coupling capacitor. CC is coupling a sinusoidal AC signal. So it's not only the call it a DC VG over here, which is being established by the biasing distances, but this coupling capacitor is also coupling the AC signal over here. You're also superimposing an AC signal over here. So this AC signal causes the VDS, because VDS, the VDS what you had is VGS minus VDN. It's not only the DC, but it's going to alternate because of the alternating signal that's present at the gate. So because of that, your VDS is going to alternate between VDS minus and VDS plus from VDS Q. So therefore, your Q point is going to shift down like this from VDS positive, and then it's going to shift up VDS negative. So your VDS is going to reduce in this direction, VDS is going to increase in this direction. Similarly, your currents, if you map them to the vertical axis, currents are also varying, and then you have this variation in a sinusoidal pattern like this. So this amplitude of this sinusoid could be greater than, call this amplitude as V naught. Okay, so this V naught amplitude could be greater than, let's say, VI, which implies that this configuration is good enough to amplify the given input signal VI, the time varying signal. Okay, so the MOSFETs can also be used as for amplification purposes, and as you can see, this amplification has to be done in the saturation region. So transistor must be biased in the saturation region in order for it to be used as an amplifier. Okay, so it has to be based in the saturation region. Okay, so you see, for a switching action is concerned, it can be like we have seen in the inverter, it can be in the non-sat region. Okay, if the input is increasing, it can go into the non-sat. Still, it can operate as a switch. Even in digital logic functions, it can be in. So this non-sat region can be used. This non-sat region can be used in can be exploited in switching actions or in digital logic functions of MOSFETs. So, but for amplification purposes, we're going to stick it. We're going to stick with the saturation region only. Okay, we're going to bias the transistor in the saturation region only. So 47B is shows the transistor characteristics and the load line that we've talked. The load line is determined for Vi equal to 0. Okay, so that's how you do it. For load line, you kill this AC source, open the transistor, then you don't have this left part. Okay, this AC part is gone. So you're only left with the biasing resistances and the MOSFETs. Determine the load line points, connect them, bring back the AC source, okay, and then find what the amplification is. Okay, so wherever this intersection occurs, that's the Q point between the IV curve and the load line. Okay, so again, 47A is the NMOS common source circuit, time varying signal coupled to the gate, and then you have the transistor characteristics, load line, superimposed sinusoidal signal. So you see. What we have an established particular Q point on the load line by designing the ratio of biased resistors, because these biased resistors R1 and R2, they are determining your capital VG, that's the DC, okay, or VGS, call it VGS. So VGS is going to set the VGS determines VDS basically. So VGS is determining your VDS. Okay, now if this VDS, because this is VGS minus VTN, is the transition point, so it determines where your transistor is biased. Okay, so once you are in the saturation region, you can use this IV characteristic. So IE is basically over here is independent of VDS. So if you consider the DC quantities, then ID is given by Kn into VGS minus VTN. Okay, so VTN is a constant, Kn is a constant, and then this is whole squared. It's only VGS, but note over here that VGS is now sinusoidal. Okay, so if you consider the AC quantity dot I, small I, with capital subscript D. Then this is a small v, capital subscript G, GS. If this is sinusoidal, if this term is sinusoidal, then of course for the constants Kn and Vtn, you're going to have a sinusoid varying, time varying ID. Okay, time varying ID, or you can say time varying VDS, right? Because if there is a time variation in ID, this is going to be translated into the time variation of VDS. So you have a output signal whose amplitude could be greater than VI is the input AC signal. But that's how you amplify the signal in saturation regions. So if we assume that the input signal is sinusoid with a single frequency, then the gate to source voltage will have a sinusoidal signal superimposed on the DC Q sync point. Now, as the gate to source voltage changes over time, the Q point is going to move up and down as indicated on the figure. So you have this string. Okay, Q point is going to move around the operating VDS and ID values. So this results in the um, changing VDS values, okay, or changing ID values. So moving up and down on the load line translates into the sinusoidal variation in the drain current and in the drain to source voltage. Okay, so over here there is a variation, and then you have the variation in the drain to source current, and that can be mapped onto the drain to source voltage through IV relationships of the MOSFETs in saturation. So the variation in the output voltage can be larger than the input signal, which means that the input signal is amplified. So that's where that's how you explain the idea behind this amplification in saturation region of operations. So the actual signal gain, it depends on both the transistor parameters, circuit element values. So you see, if you have to determine the actual gain, then you have to first of all work out the small signal model, okay, which we will develop later on. And then if it is an actual MOSFET, you need to consider the forward resistance as well. Okay, so for the given other parameters of transistor, you identify what is the exact voltage gain, and then you can find exactly how V naught is related to VI. Okay, with what ratio the output voltage has increased with respect to VI. Okay, so that's all.